Okay, last time we studied that if you've got a closed organ pipe, that is having one end closed and one end open, then the fundamental frequency and the other resonant frequencies can be given by this formula, where this is an odd number, 2n minus 1, this whole bracket is an odd number, into V by 4L. Of course, V by 4L is nothing but the fundamental frequency, right? So when you put value of n as 1, you get 1 here. When you put value of n as 2, you get 3 here, right? So let's make a table of harmonics and overtones for a closed organ pipe. Let's start. We made a similar table for string. Alright, so here I am going to write down the resonant frequency. Okay? Over here I am going to write the number of harmonic. Okay, which harmonic is it? Right? And here I am going to write the number of overtone or overtone number. Alright? So let's begin. So the smallest resonant frequency, which is called fundamental frequency. Again, just to remind this to everyone. The smallest resonant frequency is called fundamental frequency. So the smallest resonant frequency will be when we put n equal to 1 here and we get 2 minus 1 is 1. So 1V by 4L. That is the fundamental frequency. Is this clear, everyone? That is the fundamental frequency. Okay? Right. Next, this would be which number of harmonic? Again, recall the definition of harmonic. Harmonic means the fundamental frequency multiplied with some integer. So here, this is of course 1 into fundamental frequency, isn't it? This is obviously 1 into fundamental frequency. So this is first harmonic. Is that understood or not? This would be first harmonic. Clear? Okay, that's clear, everyone? First harmonic. Okay, very good. Let's go to overtone. This is not an overtone. Not an overtone, because what is meaning of overtone? Resonant frequency higher than fundamental. This is fundamental itself, it's not higher. So this is not an overtone. Clear? Fundamental frequency is not an overtone, right? Next, resonant frequency. So this was number 1. Then case number 2, we saw that we get 3V by 4L, isn't it? We get 3V by 4L. Right? So this is 3 times. This is 3 times fundamental frequency. Correct or not? So this will be which harmonic? This is 3 times fundamental frequency. So this will be which harmonic? This will be which harmonic? Third harmonic. Very good. Not second. Third harmonic. Okay. Third harmonic. Clear? Again, simple idea. બીજું નહીં વિચારો, જે કીધું છે એ સમજી લો તો આવડી જશે. Okay? What is the meaning of harmonic? Integer multiplied with fundamental frequency. So have a look here. Which integer is multiplied with fundamental frequency? 3. So third harmonic. Right? Okay. What next? Number of overtone. Again, overtone means resonant frequencies that is higher than the fundamental. So this is fundamental, and now this is the next higher resonant frequency. So this is the first higher frequency or first overtone. Is this entire number 2 clear to you? Entire number 2. Is it clear to you or not? Okay, let's go to the third possibility. Let's go to third possibility. Number 3. 5v by 4l. So which harmonic? Hurry up. Which harmonic? Which harmonic? Very good. Fifth harmonic. Well done. Fifth harmonic. Okay. And which overtone now? Which overtone? Which overtone? Second overtone. Well done. Second overtone. Do you remember once I told you that harmonic and overtone they are independent of each other? એવું કઈ ગોખવાનું ન હોય કે આ નથી 1 plus કરો તો આવે કે એવું કઈ. Okay, they are not related with each other. These are two completely different things. Got it? બરાબર એડવાઇસ આપી હતી ને? These are two completely different things. All right, so like this the list can continue. Like this the list can continue. All right, okay, so this is all we have got as far as frequency is concerned, right? Fundamental frequencies or resonant frequency for standing waves on string, on open pipe and on closed pipes, right? So be careful with that. Okay, the formulas are a little bit different. Again, I insist that if you ever get confused, draw those diagrams of standing waves. Okay, that's your best way to deal with it. Again, key things to remember about closed organ pipe: at open end there will be node, at closed end there will be antinode. Clear? At open end there will be pressure node. At closed end there will be pressure antinode, and then you can make the diagram easy, right? Okay. Now a few more points, okay, just very simple minor points to wind up everything about standing waves. Okay, then we can solve questions. We have covered a lot of theory. Okay, one or two minor points. Number one, here. In a sound wave or for a sound wave, displacement of air particles and change in pressure are out of phase by 5/2. Are out of phase by no, there is no such formula for even number. Okay, we only get odd numbers for resonant frequency in closed pipe. Okay, what does this kind of mean here? Listen to this carefully. It is that if you consider, listen to this carefully. Suppose sound wave is passing through this part of air. Compression, rarefaction, compression, rarefaction, compression, rarefaction, vice versa. Okay, listen to this carefully. Okay, when this part will get compressed, do you realize that its center line, this will not move? You get what I am saying? Do you realize its center line will not move? Okay, or vice versa when it expands. Similarly, when second rarefaction part expands, again its center line does not move. So, you know, if you are drawing two graphs, one for displacement of air and one for pressure, okay, change in pressure, one for displacement of air and one for change in pressure, then what we have is that these dotted lines that I am drawing, exactly in middle. These are the things that never move. So what would this mean is that if I draw the graph of displacement, then that graph would look like this. Okay, this would be the graph of displacement. Okay, this would be the graph of displacement of air. Let me just draw it very nicely, matching with these lines. Just give me one more. Just give me one. Okay, the graph would look like this, where this point, this point, this point, this point, and this point have zero displacement. But exactly at those points, the pressure will be maximum here, minimum here, maximum here, minimum here. Why so? I'll tell you. When this will get compressed, this point is at the center, where all the air compresses and comes to that point. So the pressure over here at this point is going to be the highest. I repeat, this dotted line indicates the line where the molecules of air will not move, right? They will neither go left nor go right. I hope that makes sense, because molecules from both sides are coming towards it. But then this line, dotted line, is where the pressure will be maximum, right? So if I would draw a graph of pressure now, black will be pressure, then where the displacement was zero, the pressure will be maximum. Similarly here, in second case, all the air particles are going away. So here the pressure will become minimum, like this. So this graph would be of this kind, where this would become zero, that would become maximum. Where this would become zero, that would become maximum, and so on. So you see, there will be a phase difference of pi by 2 between them. Why pi by 2? Simple idea. Compared to the blue graph, the black graph. Compared to the blue, the black graph is shifted by lambda by 4. Think about it. It's shifted by lambda by 4, right? Why? Because in one case where it's like this, we are getting the blue one like this. Okay, we're getting the blue one in this way. So where this becomes maximum, this becomes zero, and vice versa. So this gap is lambda by 4. I hope you see that. This gap is lambda by 4. Okay, everyone. It's half of wavelength. This is half of wavelength. Okay, and this is half of that. So half of it. Shifted by lambda by 4 means a phase difference of how much? Use that idea. Phi is equal to 2 pi by lambda into delta x. So 2 pi by lambda into lambda by 4. So lambda cancel, 2 4 cancel, pi by 2. So that's what we have written here. That there is a phase difference between displacement of particles and the change in pressure. That is in a case where change in pressure is maximum, like at this point on this line, where change in pressure is maximum, the particles simply don't move, right? Or vice versa, where the change in pressure is zero, particles move the most, right? So what this means is that wherever there is a pressure node, okay, by extension of this particular concept, pressure node is displacement antinode. Pressure node is displacement antinode, and vice versa. What this means is, where you have a pressure node, it's same as displacement antinode, and where you have a displacement node, there you have a pressure antinode. Clear? Vice versa. Remember, all this is for sound waves only. Don't try to use it for string. In string there is no pressure wave. Clear? It's only in sound. In sound you can consider the wave to be in two ways. Which two ways? One way is, you can say that this is a longitudinal wave where particles are displaced like this, left right, Okay. The other way to consider sound wave is change in pressure. Hopefully you remember the equation that I wrote last time about pressure. Remember pressure amplitude sine kx minus omega d, that equation. Right? So you can consider sound waves in both ways, like this and this. So when you compare them, what we have is the pressure node becomes displacement antinode and vice versa. Right? Yes, Mahavir, what you said is okay. Right? See, I'm clarifying this because I don't know where you are going to read things from. Different authors, different books consider it different ways. Some consider it both ways, but some only care to explain it in one way. Right? Let's see what your textbook does for a moment, and then we'll go ahead. Your textbook. Your textbook shows diagrams of displacement wave. Okay, your textbook is showing displacement waves, not pressure waves. Okay, Aditya, did you understand this first? So fairly simple. They differ by lambda by 4. So suppose this is diagram for a standing displacement wave. Suppose this is diagram for a standing displacement wave. Right? Then this is node and this is node. Then the diagram for a standing pressure wave can be drawn like this. Starting from here. Shifted by lambda by 4. I hope that is clear. Because this distance would be lambda by 4. So, where we have, black is displacement over here. So, where we have a displacement antinode at the same point, by shifting this, we will have a pressure node. I hope that makes sense to you. Alright? So, because they are shifted by lambda by 2, lambda by 4, right? It means it will shift by this much. If it will shift by that much, where there was a pressure node will become displacement antinode. Alright? Okay. More details. Let's see what is given in the textbook. See, I'm clarifying it along with the textbook only because I know that it's given and you are going to read it at some point and get confused. Right? Otherwise, there is really no need to clarify all this. Right? Okay, have a look. In your book on this page number 378, on page number 378 in textbook, you are given a closed organ pipe in figure A, B, C, D, E, F. Okay, I am talking about figure A on that page. Page number 378. Do you see a diagram like this? Everyone, do you see a diagram like this given? $382. Okay. Possible different editions have different. It's given after example 15.5 in this book. I really don't know what it would be in your book. There's no way I can tell you that. Okay, it's after example 15.5. That is antinode. Mahavir, have you been present or not for the last 3 lectures? Page number 382. Okay. Alright, thank you. Page number 382 is what we are looking at. In case it's not on 378. So a graph like this is given for closed pipe. Normally I hate to clarify for something given in the book because I would have explained it the right way. Okay, this is just correcting for other people's mistakes. Well, so this is given as a closed pipe. You see this diagram. It doesn't match with what we have drawn. Earlier, let me make you recollect what we have drawn. For fundamental frequency, we have said that open end of the pipe is a node, closed end is antinode. Okay, so the graph should be like this. But this is opposite, isn't it? This is closed end. This is definitely the closed end, right? You can see that in the diagram. So here they have shown a node and here they have shown antinode. Are you seeing that these two don't match with each other? Are you seeing that these two don't match with each other? I hope everyone saw that, otherwise this explanation is of no use for you. Okay? If you didn't realize that these two are different, then what I am going to tell you is of no use. Here at open end they have shown antinode. Here at open end we are showing node. Here at closed end they are showing node. And here at closed end we are showing antinode. Chane undu, ke nadi undu. Okay, why is it like that? The reason is they are drawing displacement wave for sound. I repeat, they are drawing displacement wave for sound. And we have drawn pressure wave. Hopefully you remember that I only explained about displacement wave for sound today. Right? Before this day I didn't even mention about displacement wave for sound. We were just talking about pressure. Correct or not? So now read this sentence and look at these diagrams and with these explanations. Everything falls in its place? Everything okay or not okay? Did you understand both the diagrams? Pressure node is displacement antinode. So where there is a pressure node here, at open end there is displacement antinode, and where there is a pressure antinode at the closed end there is a displacement node. Understood? એટલે કોઈ જુદું નથી. એટલે આવું જોઈને એવું ન કહેતા સરે તો ઊંધું લખાયું હતું, અમે બહુ હોશિયાર છીએ. તમે હોશિયાર નથી, તમે બરાબર સાંભળ્યું નહીં. ઓકે, be careful. It's not wrong. What I have told you is not wrong. What given in the book is also not wrong. But these are just two different ways to represent the same thing. Okay, so don't get confused ever. Alright. We can draw any one. Yes. अरे क्या भाई तार बोर्ड एग्जाम में ड्रॉ करવું છે? 11th માં તો તને માસ પ્રમોશન મળ્યું. ક્યાં ડ્રો કરવા દેશ તું? Question mark. Question માં તો તમારા માટે ડ્રો કરવાનું હોય. If you can use your diagram to solve the question, that's it, right? For reference. Yes, so you can draw any one. That's right. That's what I've been saying. Both are correct. Okay? Once I say that both are correct, then I don't think the question of which one to draw should arise. Don't you think, everyone? If I would have said no, this is wrong and that is correct, then only you should have worried. Right? Anyway, okay. So with that being out of the way, hopefully this will avoid confusion for everyone. Okay, if you ever see the book. Alright, now let's solve questions. Alright, the first example related to this concept is 15.5. Okay, first example related to this concept is 15.5. Okay, a pipe is 30 centimeter long, is open at both ends. Alright, a pipe is 30 centimeter long, open at both ends. Which pipe, open or close? Come on. Which pipe, open or close? Example 15.5, everyone. Which pipe, open or close? Open, very good. So we know it's an open pipe. Okay, let's draw a diagram. Right, here's the diagram. Length is given to us. How much length? 30.0 centimeter or 30 centimeter. Fine. Which harmonic mode of the pipe resonates at 1.1 kilohertz source? Okay, what does this mean? Listen to this. There are special devices. If you remember, I told you about something like a tuning fork. Remember this? It vibrates, right? So, if we put a tuning fork here which vibrates at how much frequency? 1.1 kilohertz. Okay, it vibrates at 1.1 kilohertz. Alright? So, when you will put this here, sound will pass over here and there will be standing waves. Right? That's the thing given. Sound will pass through this and there will be standing waves by the reflection and all that. Okay, now we have to find which harmonic would this be. We have to find which harmonic would this be. Okay, so first of all, this frequency is how many times fundamental. That's what we will find out. Okay or not okay? This frequency is how many times fundamental. So, let's do it as follows. For open pipe, what is formula of resonant frequency? Time to use our formulas. Come on. Harmonic mode means which harmonic? Okay, that's it. Alright? Harmonic mode or resonant mode, all these are synonyms. So, this we will compare with NV by 2L. Is this clear or not clear? Is this clear or not clear? NV by 2L. Yes, no problem, Marvin. It's fine. Starting again. Okay, so NV by 2L, right? Okay, which information do we have? Take speed of sound in air as 330 meter per second. Alright, so let's put everything. Therefore, 1.1 into 10 raised to 3 is equal to n into 330 upon 2 into length 0.3. Okay, right? Alright, everyone. See, we can do this very easily here. I will make this 3 and I will make this 3300. This cancels here 1100. This is 1100, that's also 1100. N is equal to 2. Clear? Everything cancelled. N is equal to 2. Clear or not clear? N is equal to 2. Okay. So, N equal to 2 means this frequency, which is 1.1 kilohertz, is actually 2 times V by 2L, isn't it? It's 2 times V by 2L. Means which harmonic? Come on, everyone. Which harmonic? Which harmonic? Second harmonic. Very good. Second harmonic mode. You could write it like that. Okay. And which overtone? Which overtone? Second harmonic mode, correct. And which overtone? First overtone. Very good. That's right. First overtone. Alright? Fine. How did you know? Easy to get it. Next thing. Here, there's one more question. Let's read that. Will resonance with same source be observed if one end of the pipe is closed? Okay, now understand this carefully, everyone. What is given? What is given is that now we close one end of the pipe. So part B kind of thing over here. Closed it. Alright? And then same source. So as long as source is same, frequency will remain same. Did you understand what I am saying? As long as source is same, frequency will remain same. Yes or no? Okay, now what's the question? Let's read it carefully again. It says, will resonance with same source be observed if pipe is closed? So now the question means that if we close this end of the pipe, now will there be resonance? Okay, simple question, will there be resonance? Yes or no? So how to decide? Listen to this. How to decide? Is this frequency in the list of resonant frequencies for closed pipe? If yes, resonance will occur. If not, resonance will not. I repeat, is this frequency in the list of the resonant frequencies for closed pipe? Okay, so what's the formula of resonant frequency for closed pipe? What's the formula of resonant frequency for closed pipe? General formula for resonant frequency of closed pipe. Be careful everyone. No. Resonant frequency, not fundamental. Resonant. Yes, very good. Many of you have given right answer. Well done. Yes. 2n minus 1 V by 4. Okay, it should match this. It should match this. If it matches that, it is going to happen. Resonance will happen. Right? Resonance will occur. If it does not match, resonance will not occur. Clear? Plan is clear. If this matches with this, then resonance will occur. Otherwise, it will not. Got it? Okay. Now there are two approaches. There are two approaches to solve this question. First, I'll use a simple approach. Okay, not formula based, right? Very common sense based approach. Okay, have a look. Listen to this carefully. If you think of the list of the resonant frequencies for closed pipe, it is V by 4L, it is 3V by 4L, it is 5V by 4L and so on, isn't it? Yes or no? So can you find V by 4L for me? Come on. V by 4L. Can you find V by 4L for me? How much will be V by 4L? 330. Speed of sound 330. 4. Length is 0.3. How much will this be? Come on everyone. How much will this be? How much will this be? Yes. 275 Hertz. Correct. So this is the fundamental frequency. Right? 275 Hertz. Alright? Okay. Now, what will be this one? See, this is into 3. So 275 into 3, 600 and 825. Isn't it? Clear or not clear? 825. Alright. Then this one would be this into 5. So 1350 and 1375. Is that right? Check it. Is that right? Four one two five. Are you sure? 4125? No, it won't be 4125. Ria, you are multiplying this with 5. That's wrong. You have to multiply this with 5. 5 into V by 4. Did you all get 1375? Yes or no? Did you all get 1375? Okay. So, this is the list. Now the frequencies will be even more. Don't you think? Frequencies will be even more than this. I am not finding it. Okay, in this list, do we have 1.1 kilohertz? Means 1100 hertz. Do we have this in the list or not? Do we have this in the list or not? It's not in the list. What that means is that, listen again, for this frequency you will get resonance. I repeat, for 275, for 825, for 1375, for the next you get resonance. But for 1100 you don't get resonance. Understood? So the answer to this question is resonance will not. Clear or not clear? Clear or not clear? Okay? But let's do it by another approach. I know this is a very simple approach, right? I'm sure everyone would have understood that, right? But let's try another approach, slightly more, formula based, a little bit of maths, but shorter than this. See, what we'll do is we will just compare 1.1 kilohertz with 2n minus 1 V by 4n. Okay, I don't know whether this is right or not, but I'll compare. I don't know whether this is right. I will compare and I will see what happens. Okay, let's put all values. 1100 equal to 2n minus 1 V by 4n 275. Isn't it? We already have found it. Why do it again? Right? Divide this. Divide. Come on, tell me what do you get? 2n minus 1. It will be equal to how much? 1100 upon 275. How much? 4. Very good. 4. 2n minus 1 is 4. Therefore 2n is 5. And therefore n is equal to 5 by 2, which is 2.5. But that's cheating. That is contradiction. If you recollect this formula, what was n in this formula? What was n in this formula? What was n in that formula? N is supposed to be, read it, n is 2. Hey, એવું ક્યાં લખાયું છે કે n is 2? Read that carefully. Come on people, don't say n is 2. Read that carefully. What have we written in that formula? N is integer. Yes, n can be 1, 2, 3, 4 and so on. Can n be 2.5? Can n be 2.5? No, of course not. Alright? So that's why this is wrong. Did you understand? We are getting a contradiction. First we assume that, okay, suppose it's resonant frequency, then what should happen? Then we should get n equal to 2.5. No, not valid, not allowed. Okay, but n has to be integer. So just you can write it here. Okay, but n has to be integer. So this frequency does not cause resonance. Did you understand what we are writing? Right, but n has to be an integer, so this frequency does not cause resonance. Clear? The second method over here, absolutely clear? Short, but yes, the idea here is simple. We just see the list and we decide. Okay, so hopefully you have understood both the methods, right? Let's go to the next question. Okay, in the exercise, everyone, in the exercise, question number 11. Question 11 from exercise. Yes, Margaret, absolutely true. If this was, suppose this turns out to be integer, let's say by some other number here, some other number was given, and suppose we got n equal to 3, hooray! That means this is resonance. Clear? Okay? If suppose we got an integer, then that would mean it's fine. This will be resonance. Alright, exercise question 15.11. Right. So transverse displacement on a string clamped means fixed at both ends. Transverse displacement of a string clamped at its both ends is given by y is equal to, okay, you can write y of x and t, no problem. Y equal to 0.06 sine 2 pi by 3x and cos 120 pi t. Okay. First of all, observe the equation. Does this equation look like number 1 or does it look like number 2? Pick your choice. Come on. Does this equation, given equation, look like number 1 or number 2? Does the equation given here look like number 1 or number 2? Very good. 2. So it is equation of what? This equation is of which wave? This equation is of which wave? Which kind of wave? We have studied two kinds of wave in this chapter so far, right? One is traveling wave and the other is standing wave. This equation is of which kind of wave? Yes, standing or stationary wave. Very good. It's of this pattern. Correct? This is equation of a standing or a stationary wave. Right? So answer the following. A. Does the function represent a traveling wave or a stationary wave? Answer. Stationary wave. Correct? The answer of A is standing or stationary wave. Alright? Okay, second part. Interpret the wave as a superposition of two waves traveling in opposite directions. What is the wavelength, frequency and speed of each wave? Okay, so what does that mean? Okay, I take you back to the derivative. Everyone, go back to how we derived this formula. Do you remember that we actually added two waves, one going towards the right side and along with that one going towards the left side? Do you remember this, everybody? Okay, right. So what is this B question telling you? It's telling you to find out both these equations separately. It's saying that find out these two waves that superpose and we get this wave, right? Okay, so first of all, before jumping on to that, let's analyze this and compare it. So, do you realize 2A is 0.06? Yes or no, everyone? 2A is 0.06. So, A should be 0.03. Clear or not clear? Okay, and some unit will also be given. What was the unit given? Meter. Okay, very good. Meter. Fine. Next comparison. Kx. Kx. So what do you think K is? What will be K's value by comparison? What will be K's value? 2 pi by 3. Do you remember unit of K and name of K? What is name of K? What is unit of K? What is name of K? What is K called? And what is its unit? K is called force constant. Ami, in waves, K is force constant. No, they were. Naam bhuli kya? Yes, Raj, that is one of the correct names. K is called angular wave number. I am writing name here. Angular wave number or propagation constant, because it tells you in which direction wave is going, doesn't it? These are two names of K, and the unit is SI unit is radian per second, right? Okay, everyone, like which was it? Radian per second. Clear? Okay, so K is done. Next, omega. Now, I'll not take a lot of time. Clearly, omega is 120 pi. Actually, this would be radian per meter. Excuse me, I made a mistake. It will be radian per meter. This omega has unit radian per second. Okay, omega has unit radian per second. K has unit radian per meter. Formula याद रखिए तो यूनिट में वांधो न આવે. K equal to 2 pi by lambda, right? 2 pi is an angle. Okay, so radian and wavelength is in meter. Okay, fine. Hopefully everything's clear. Now we can easily make this equation, can't we? We have all the details. Can you fill in the details on your own? All right. Okay. Fine. Let's go to. There's something more here. Also. There's something more here. It says, what is wavelength, frequency, and speed of each wave? Oh, group H. K we know. Can you find wavelength? Yes or no? खाली એટલો જ answer જોઈએ. Can you find wavelength? Yes or no from K? All right. Then from omega, can you find frequency? From omega, can you find frequency? What is relation between omega and frequency? What is relation between omega and frequency? Others, come on. Omega equal to 2 pi f or f equal to omega by 2 pi. Right? However, you do. Okay, and speed of wave. Can you find speed of wave? Using this and this also you can get it. Right? I hope you remember this formula. V equal to omega by k. Suppose you don't know that, then I'm sure you know this. V equal to f lambda. Okay? આવડી જશે ને હવે તો? Alright. Now, last thing that we are going to do for today. C part of this question. Determine the tension in the spring, right? What does all this have to do with tension? Let's see. We would have found V, wave speed, right? This is which kind of wave? Transverse or longitudinal? Come on, everyone. Which kind of wave? Transverse or longitudinal? Transverse or longitudinal? Transverse wave. Very good. So can you relate for a transverse wave? Can you relate tension with wave speed? Is there any relation for a transverse wave where tension and wave speed are connected? Yes, right. Correct. Is there any relation where these two things are connected for a string? Tension of string and speed of wave. It is V equal to under root P by mu. Right? V equal to under root P by mu. Okay? What's that? T is tension and mu is mass per unit length, right? And I'm sure all the information is given in the question. All right? I'm sure all the required information is given in the question. You would have found V from here. Only then you can do this. Okay? So that's what we have for this C. Now I just want to add one more question to this, everyone. Don't go anywhere. I just want to add one more question to this. Which harmonic will the string oscillate in? So you have to find the harmonic number. Given the information in the question, you have to find the harmonic number. That's your extra question related to this. Okay? Note it down and then I will end the class. Raise your hand when you are done. Raise your hand when you have noted it down. Okay. Alright. Fine. Goodbye everyone. See you all later.